Okay, so the big step semantics. Well, as I said, there are two types of operational semantics. The idea of the big step is to you start from initial state, you execute the program, and then you get the result. So this is a bit like running an interpreter, so the Java interpreter or something. And the small step semantics will execute only one step of the program and would leave you with the rest of the program to execute. And then you give it again to the small step, and then it continues and does one step. So you can think of it as more like a debugger, right? So it's like an interpreter, but it can stop in the middle until you, okay, I have done this much, I am in this state, and I have this left to do. And you'll see, so all the semantics resemble idealized things that you know. So the operational semantics, they have the feel of an interpreter. We're going to see that the denotational semantics is a bit like a compiler instead. And the axiomatic semantics or core logic is a bit like a verifier. And if you want to specify a language and you know nothing about logic, well, a very natural thing to do would be to write a reference interpreter or a reference compiler, less often a reference verifier. And well, this is exactly what we're doing here, except that we're doing it in the language of mathematics or the language of logic. So that's why I say idealized, right? So we start with the big step semantics, which is our interpreter, if you like. And the interpreter is basically a predicate of this form here. So it starts in a certain state, big S. Oh, sorry, it starts with a statement, big S, in a state, small s, and it leaves you in a state, little t, right? So starting in a state S, executing in S, terminates in a state T. That's how we're going to read it. And here have a concrete example. I've written the program here not in lean syntax, but in intuitive usual syntax. I have only one semicolon here, and I don't have the stmt.assign and so on. And the same thing for the states, right? So this is a state where x has value 3 and y has value 5. It's just an informal notation here in the comment, right? So we have this program to execute. We have this state. And then at the end, we're in that state. And that's pretty easy to see if you compute 3 plus 5 is 8. You put that in x, y is 0. So you end up with x is 8, y is 0. So what I've just done is very informal because, I haven't said yet how to interpret assignment. What is the semantics of assignment? And this is done by the derivation rule. So this is a bit like the typing system, right? The type system that we saw in lecture 1 and refined in lecture 3. You have these, horizontal bars. It's a formal system. It's a system that tells you under which conditions you're allowed to derive these judgments, these predicates. And that's how, semantics, at least operational semantics, are usually specified in literature with these rules and these horizontal bars and so on. So let's look at them in turn. So you have the skip rule, which says if you start with skip in the state S, you end up in the same state. That's very important. So if you have a typo here and you write S prime, then that rule says you can start in any state S, execute skip, and end up in any state S prime, completely arbitrary. So you can, skip basically becomes a complete randomizer of your of your state, which is not what you want. So you have to be extremely careful when typing in those rules, and you have to prove some properties about them to as a sanity check. Make sure to make sure that you've well, as much as possible, that what you've written here corresponds to what you have in mind, because there's no way a proof assistant can do it for you. So you start with the C specification, you formalize the C specification. There's no tool that can guarantee that what you have is really a C language specification. You need, for that, you need several pairs of eyes, you need tests, you need lemmas, and so on. And even then, you're never 100% sure. You cannot be, because it's that's where you do the transition between the real world and the world of logic. And that transition is always a leap of faith, at the end of the day. Okay, here you have the assignment rule. So we assign A to X in a state S. And then what we obtain is a state where we update the value of X in that state to be what happens when you evaluate A in state S. And those are just ad hoc notations, right? So this is the value of A in state S. It's and this is an operator that updates S, which says, well, the state S is going to be identical as before, except for variable X, which now will be that. And you see here, the nice thing is you see explicitly that, you use the same state to evaluate here, and then this is the state that you modified then, right? So if you put S prime, then this would be some other state. So you see the state clearly, the two uses of the state here, whereas here it's implicit, right? It's just syntax. Nothing tells you in which state you're going to evaluate A or in which state you're going to end up afterwards, right? So we're really defining the semantics of the statements here. Sequential composition is, well, we start at the bottom again. So if we want to show that, if you have this program, which is a composition, and you start in state S, and you end up in S prime prime, well, to have that, it suffices to be able to execute S and to end up in S prime, and then to continue from S prime with the other program there, and to end up in S prime prime. Okay. Then you have if then else, for which we have two rules, right? So you see you have two rules with the same conclusion. This is not a problem. That's a nice thing with inductive predicates. You can always add rules, can always remove rules. The thing will I mean, each rule is seen in isolation. And then, so you don't have to worry about being deterministic or something like you have when you do pattern matching. So in the case if true, well, what happens is if the condition is true, which is a side condition I've put on the side here because it doesn't have the form of a judgment, we put it on the side, and it restricts the instantiations of B, so which B's we can put there. Well, if it's true, then we're going to execute S. Right, and this is what the premise says here. So we take big S, we execute it in the same state as we have here, we get a new state S prime, and this is going to be the result of the whole if then else. Because an if then else where the condition is true, should behave exactly the same as the program S alone. And here you have, of course, the same with S prime. So if the condition is false, you put S prime. And you have, again, to be very careful. I mean, if you just write this, then the rule is wrong. So you have to be very careful again. Okay, then you have while when the condition is true. So we say, and again, it's a bit like a composition in some sense. If the condition is true, what you do is you first execute S, and then you execute while again, right? And then you have the same game with you go from S to S prime to S prime prime, and you end up in S prime prime. And while false is very easy. It's just like a skip, which shows that we don't really need a skip in our language. We could always create one if we wanted, but it would be a rather ugly one. So it's better maybe to have a skip after all. And now, how do we translate this to lean? Well, this will be maybe my question at the exam, but here we already have the answer. It's given here. And this, unfortunately, looks quite ugly. It's like a big block of text, but it's actually extremely close to what we have upstairs, right? So if we look at the skip rule, unfortunately, I cannot use the nice arrow here. Right, what I would like to write is this, and I cannot write it yet. Actually, the arrow I want to use is the long one, sorry, because it's a big step semantics. We use a big arrow. So unfortunately, I cannot use it yet. I mean, if you look at the bottom of the screen, you'll see that it's coming, but lean doesn't allow us, at least lean 3 doesn't allow us to define nice syntax immediately. So here we see, we start with a skip. We in a state S, and we end up in a state S. This is exactly what we had upstairs. This is the assign, and the notation is a bit different, but if you want to evaluate an expression A in a state S, right? So previously we wrote S of A, but actually in Lean it's A of S, because A is a, it's a lambda expression, or it's a, well, typically a lambda expression. It's a function that takes a state as argument, and you have to pass the state, and then it will evaluate itself. So the syntax is backwards here. And we use these curly braces for the update syntax, which is not entirely standard, but we have to because of technical reasons. So here we have an example of a big step of sequential composition, right? So we want to show, here it's called a bit differently, so it's S and T instead of S and S prime. That's easier for me to pronounce as well. So it's, so we start, if we want to derive this, then we have to derive this condition here, that you can go to T first, and then that you can go to U, and then you can go. So instead of S prime and S prime prime here, the more reasonable names were chosen. So I think for next year, I'll do the same upstairs. And so on and so forth. So this is really just a direct coding of everything we saw. The side conditions are here as well. So hcond is the side condition, for example, that B is true in the state. So again, it's just like for arithmetic expressions. You have A of S here, here you have B of S. Here the condition is false, here the condition is true, here the condition is false. And that's how we encode things. And now we define, right, so this is just black magic. You don't have to learn it, but we define the arrow abbreviation, a syntactic sugar for the big step predicate.